cancellation of congruences, we hinted at this a couple days ago when I told you that we were going to someday utilize this theorem, but this was one of the theorems that we used for simplifying the modulus, is if you have a value times A, value times B, and those are the same values, mod M, your GCD of C and M, if it's D, you'll be able to divide by C and divide by that GCD of D. And so that is the only time, and we've talked about this with that prime example, it's the only time you can divide this by that GCD. You can't just divide by anything you want. It has to be a GCD of not only what's divided by both A and B, but by the module itself. The proof of that is changing it into a linear expansion. CA is equal to CB plus KM. K is an element of the reals. And we've done this 100 times. And then what they did is when they said this part here, GCD of CM equals D, then D has to divide C, and D has to divide M. So you get C is equal to R times D, and M is equal to, see, I need to change this view quick. M is equal to S times D. So then you get this brand new expansion here. Remember, CA is equal to CB plus KM. And then since C is equal to RD, we put this RD here, we put this SD here, and then you're going to get RDA equal to RDB plus KSD. What is in all three of these? A D, right? So you can take these D's out and get RA equal to RB plus KS. And then they just moved this to the other side. And so you get RA minus RB equal to KS. Factor out the R's. And you get R times A minus B equal to KS. So then what happens there, did I do that right? Yeah, K times S. Then what happens is that you can say that S divides R times A minus B. And S and R relatively prime, you can say that S divides A minus B, and that's the thing that we're going to divide out of the M. We're going to divide that D out, and that proves this one. And I don't know if I explained it super well, but what you're looking at is you're showing that this GCD can divide out the M if D is the greatest common divisor right here. If this is the case, you're going to be able to do that. If you have a GCD of CM is the only condition when you can divide by that D. And we'll use that for solving. Some of the offshoots of it, if it is 1, Andrew asked about that, then it's just A congruent to B mod M. But if P doesn't divide C, then it's going to keep that module of P. All right, and here's some examples that they gave. 33 congruent to 15. Let's see here. Take this first one. They said GCD of, well, first of all, what can you divide 33 and 15 by? 3. So that's going to leave me with 11. Yeah, they have 11 times 3 and 15, 5 times 3, and 9. Does 3 and 9 have a GCD? Of course it does. It's 3, right? So since it does, then you can change this expression to 11 is congruent to 5 mod 3. And that's nice because that'll be a lot easier to find your solutions for. And 11, is 11 congruent to 5 mod 3? Is it? 11 minus 5, what's that? 11 minus 5, 6. That's divisible by 3. But take a look at this next one. The next one here, you have negative 35 and 45. I can divide negative 35 by 5 and 45 by 5. And that's going to give me negative 7 and 9. But what's the GCD of 5 and 8? Okay, 1. So what that means is if you divide by 5, you don't divide the 8 by 5. So you're going to get negative 7 is congruent to 9 mod 8 over 1, which is 8. And if you take, let's see, let's add 8 to this. Negative 7 plus 8 is what? 1. Is 1 minus 9, is that divisible by 8? Or add 16 to this. Is 16 minus 7 is 9. 9 is congruent to 9 mod 8. So now it works out. But you don't divide that. So when you look at congruences here, just remember when to divide m. When can you divide m? When can you divide this? Well, it's when you have a D where D is equal to GCD of C comma M. This is going to help us. Now, for solving the equations, we have already talked about it. You've got this linear thing, AX is congruent to B, and you want to find X. It's kind of clunky, but it's going to be interesting. All you need to do is you need to, by inspection, that means you just kind of look at it, see if you can find an answer, find that x0, and then if you have this division situation, for example, 4x congruent to 8 mod 12, what's the GCD of, what can we divide both these by? 4 comma 12. It's 3. Okay? So can you, or 4, not 3. They said it, computer, not me. All right, so 4, 12 is 4. So this is the equivalent to 4x over 4, or x is congruent to 2 mod. Now, can I take 12 and divide by 4? Absolutely. So there's where your 3 is. That's what you were thinking of. And so here's what my question is. What answers are going to work for x now? What answers are going to work for x? You know, if I just look at this, yeah, it's just going to be, I would say, x is equal to 2 is an easy one, right? And what's that? Yes. Right, right. So what you're going to do is you're going to say, okay, I can have x equal to 2, and then what else could I have? 5, 8, and 11. And why can't I keep going? Because what's our mod? 12. And so there's your 2, 5, 8, or 11. Now, they go about it a little differently. What they do is they find first, x0. Then what they do after that is they set up x equal to x0 plus whatever your m over d is times t. And you just get all of these multiples all the way up to the m. And so t is going to be 0, 1, 2, all the way up to well, it's going to be m over d minus 1. And you just put those in for t. And they prove that on this next slide. Should I go through this full page proof? I'm not going to, but you can go through it if you want. But you can see how they started off with the Diophantine equation of power 1, and they used this idea of GCD-AM, GCT negative M, and that's where they build all of these alternate values, all these alternate different congruent answers less than M. And then once you get to that, you can see how they built the dynamic of the greatest and the least. This is what we talked about here. We talked about the M over D. And so when it's all done, you're going to have x0 plus M over D times R. And R started out at 0, then it went 1, 2, all the way to, what was that, M minus 1? No, D minus 1. D minus 1. So I think we've done enough of these, except I want to do B. So would you take out your iPads? Would you go to example 32B? We're going to do B together and just show you how easy this is. 12x is congruent to 24 mod 54. What's the GCD of 12 and 54? 6, right? It is 6. Okay. So since that's our GCD is going to be 6, then T is going to be 0, 1, 2, 3, 4, 5. Why not 6? Because that we have the 0. So you have that one already. Okay. Now we just need to find, can we divide this by 6? Yes, we can. So this is going to be 2x is congruent to 4 mod 54 over 6, which is 9. Okay? So we're going to find your x0 first, and we'll, what? 2? I divided 12x by 6, all these by 6. Because we showed that GCD being 6, then, and these are divisible by 6, yeah. Okay, then your x0 is 2 plus nine t. Okay, so then your answers are going to be x is equal to 2. The next one will be what? 11, then what? Well, it's too high for 9, but not 54. Yep, and so you're going to add 9, 20, 29, then what? 38, and then what? 47. Is that it? What? Those should be all your answers. Mod 54, not mod 9, mod 54. Doing okay? All right. Now, if we go back to A, A is just 2x congruent to 3 mod 5. This is A. Now, the reason I want to do this last is because what's the GCD of 2 comma 5? 1. So what does that mean? Can't divide it down, so therefore you're going to have 2 times what congruent to 3 mod 5. What's going to work for this one? Is it 4? 8 minus 3? Yeah, so 4. So x0 is equal to 4, but that's all we're going to have. 4 is the only one that's going to work. Because what happens if you added 5 to that? Now it's over, and so it's just a redundant answer. So 4 mod 5, this is as high as you go. 4 mod 54, do you see why I had more than one answer? Okay, kind of brings me back to, remember when we did sine 2x equal to like square root of 2 over 2, and we found it for 1, and then we did the 2x equals, and we doubled it and all that stuff? No? Well, you probably do. You probably do. Mark.